Okay, so at this point in the course, we have quite a big change in topics. We're not going to be looking at integrals now for quite a while. Instead, we're going to be looking at infinite sequences. Okay, and then shortly afterwards, we're going to be looking at infinite series. Now, the two are going to definitely be related to each other. And by the two, I mean series and integrals. However, we're not going to see that connection until we get to what's called the integral test. So for now, let's look at our introduction to sequences, and then we'll relate sequences to infinite series. So first off, what is a sequence? Well, a sequence ultimately is just going to be an infinite set of numbers, except that it has a specific order to it. Okay, so it's an infinite set and it has a given order. Now, that means that one, the set never ends, okay, it just keeps going on and on and on, but it does have an ordering to it, meaning there is a first term, there is a second term, there is a third term, and so on. And typically what we're looking at with a sequence is that there's going to be a pattern to the actual sequence, okay, and the pattern is going to be sort of represented in this term here, okay, this is going to be the general term. And so for this example sequence, we can tell we have here our first term. Okay, this is when n is equal to 1. And then we have here n equal to 2, n equal to 3, and so on. We want to know what's going to be the pattern. Well, the pattern is given by n over n plus 1. And you can see that by just sort of breaking down the sequence into its different components. We have the numerator and we have the pattern for the denominator. So the pattern in the numerator is just 1, 2, 3, 4, very straightforward. That's simply just given by n, okay, and n here is essentially the counter for our sequence, okay, starting at 1, going to 2, going to 3. So there we have our numerator, pattern given by n, and our denominator, not terribly different for now, but you'll notice if n is equal to 1, then our denominator is equal to 2. And if n is equal to 2, then our denominator is equal to 3. And so our denominator, the pattern here is going to be given by n plus 1. So really, what we're going to do for this is you could write your general term an, and it sort of represents on its own all the information collected in the actual sequence. And so really you could say that your sequence is given here by an, okay, and again this is our pattern for an. Okay, n is going to be starting at 1 and going to infinity, and we have that for both of them. Okay, so these are sort of the different ways that you could represent your sequence. Okay, you could represent it like this, okay, with all the terms actually sort of written out, or with many of the terms written out, or you could just use the general term. So the first few questions that we look at for sequences are going to be very much related to this. We're going to be looking at essentially pattern recognition. Okay, so we're going to be looking at sequences, trying to figure out what the pattern is, trying to figure out what the general term is going to be. So here, let's take a look at these three. Find a formula for the general term for each of the sequences. We're looking for an. So in this first one, okay, what is an going to be? Again, we have a fraction everywhere, okay, so we know an is going to be a fraction. We want to figure out what's the pattern in the numerator, and then what is the pattern in the denominator. So first off, let's look at the denominators because they're a little bit easier, okay. If you'd like to, you can sort of pair these off to remind yourself, okay, this is n equal to 1, n equal to 2, and so on. So if n is equal to 1, our denominator is equal to 2. Okay, and you'll see right away this pattern in the denominator still n plus 1. That's similar to the one we were just looking at. But what's the pattern here in the numerator? If n is equal to 1, our numerator is equal to 1. If n is equal to 2, our numerator is equal to 4. And if n is equal to 3, our numerator is equal to 9. So I want you to sort of pause the video, think about this for a few minutes. What pattern do you recognize? And here you should recognize that that numerator, the pattern is just given by n squared. Okay, we have 1 squared, we have 2 squared, we have 3 squared, 4 squared, and 5 squared. Okay, so this is going to be our general term for the sequence. It represents the pattern in our sequence. So now let's take a look at B, and we want to do the same thing. Okay, what I would recommend for you is to again pause the video, take a look at B, okay, see if you come up with the pattern. What's the pattern in the numerator? What's the pattern in the denominator? So looking at the numerator, okay, here we have 3, okay, and again, that corresponds to n equal to 1, and 6 corresponds to n equal to 2, 9 corresponds to n equal to 3. So you could see this sort of in two different ways, I would say. In the numerator, what we have are multiples of 3. Okay, every time that n increases by 1, our numerator is going to increase by 3. Okay, so really in our numerator, we're going to have 3 multiplied by n, and that actually works out perfectly. If n is equal to 1, our numerator over here is equal to 3. If n is equal to 2, our numerator is 6, and so on. Now, what's the pattern in the denominator? There we have 5, we have 25, we have 125, and so now we are looking here for the patterns, or sorry, for the pattern there, and those are just going to be the powers of 5. So we have 5 to the power of n, and that is our general term for this sequence. Now, this third one, okay, it's quite interesting, but it's definitely a step up in terms of difficulty. What I would recommend, pause the video again, think about this one for a few minutes, try to come up with the pattern, okay? And really, what I would recommend, if you want a hint, okay, try to find the pattern in these terms, okay, and then see if you can make that pattern work for these terms as well. All right, so here, again, let's sort of make sure that we have these set up. This is n equal to 1, n equal to 2, n equal to 3, and let's do one more, n equal to 4. Okay, so these are the different terms that we're looking at. We want to come up with a pattern. In the numerator of just these 3 here, we notice we have 4, 8, and 16. So every time that n increases by 1, okay, that is actually not increasing by a set amount, but those are definitely the powers of 2, okay? This first one here is 2 squared. This is 2 to the 3. This is 2 to the 4, okay? So in our numerator, we're going to have something like 2 to the power of n, except that on its own, that doesn't work, because you'll notice here, when n is equal to 3, our number should be 2 squared. So what we have instead of 2 to the n is that we have 2 to the n minus 1. So that's going to be our numerator. That will work for this term. And also if n is 4, we get 2 to the 4 minus 1 will be 2 to the 3, which is going to give us 8. Okay, so that's our numerator, 2 to the n minus 1. Now if we look at the denominator, we have here 3, we have 9, and we have 27. Those are also going to be the powers of 3, except it's not going to be 3 to the n either. In this case, if n is 3, I would like my denominator to be 3 to the power of 1. So that's going to be 3 to the n minus 2. Okay? And that will work for n equal to 3. And if n is equal to 4, we end up with 3 to the 4 minus 2 would be 3 to the power of 2, would give us 9. So that pattern is going to work for these terms. Let's take a look, though, does it work for these starting terms? So first off, if n is equal to 2, our term should be just 2 itself. So actually, let's look at what happens in the numerator. If n is equal to 2, we get 2 to the power of 1, which is fine. And in our denominator, if n is equal to 2, we will get 3 to the power of 0, which is going to be 1. So we will have 2 divided by 1, and that's going to give us our term 2. We will also notice that if n is equal to 1 itself, what happens? Well, we end up here with 2 to the 0 is going to be 1, and 3 to the 1 3 to the 1 minus 2 will be 3 to the negative 1, and 3 to the negative 1 is actually just going to be, or 1 over 3 to the negative 1 will just be 3 itself. So that works out for the first few terms as well, even though that pattern is definitely much harder to recognize in these two terms than it was in these terms later on. So that one is just sort of an interesting question, looking for the pattern. Now, let's sort of take a look at one more question, okay? And this is really where the topic of sequences is going and how it's going to lead us to looking at infinite series.